Okay, so what we want to do is we want to show how we can get something called the heat equation. So the heat equation is going to be this equation, except rho, instead of, for the unknown function, it'll be u, you'll see in just a minute. Instead of measuring the density of something, it's going to measure the temperature of the rod. Because if rho measures thermal density here, then I think it makes more sense to measure thermal energy density, whatever that might even mean, with a thermometer rather than something else. Okay, so what we're going to do here is if rho is thermal energy density, and u is temperature, u of xt is a temperature at location x at time t, and u is temperature, then how are they connected? Then how are they connected? And they are connected through something called specific heat. So, the specific heat, C, of a material is the amount of energy needed to raise to raise 1 unit of mass 1 degree. So it's the amount of energy needed to raise 1 unit of mass 1 degree. And in general, C is a function of the material. So X would be like the material. If we have a heterogeneous rod, location X is going to give us a different material. And it's also, so C of X means it's dependent on material because the material can change. But it's also dependent on the temperature U. Okay. So how can we use this to relate the density to the temperature? Or sorry, to relate the thermal energy density to the temperature. Well, let's imagine we're looking at a very small section of the rod. Let's say from point x1 to point x1 plus delta x. We're thinking about this as being a small portion of the rod. Now, the thermal content, the amount of thermal energy, so thermal energy is equal to rho, well, it's approximately equal to rho of x1 t times delta x. Okay, we're assuming it's so small that like the energy density is constant, the temperature is constant, that it's basically just completely homogeneous. Okay, so the thermal energy is approximately going to be equal to rho of x1 times delta x. Okay, rho is the energy density, so energy density times length gives us energy. Okay, on the other hand, we know that the temperature is U of x1t. And using the specific heat here then, the total energy has to be C of x1 U times the mass of this piece, okay, times the temperature. Because if it is at this temperature U of x1t, then and specific heat is the amount of energy needed to raise the temperature if the specific heat is the amount of energy needed to raise 1 unit of mass, 1 degree, and we know it's at U degrees, this expression is going to be the amount of temperature in that section of the rod. Now what we're going to do is we're going to introduce the mass density function. So m of x is equal to the mass density function. So the mass of the rod going from x1 to x2 is the integral of m. So that's the mass density function. So this is going to be approximately equal to c of x1u times the mass, which is approximately going to be m of x1, that's the mass density, times delta x, and then times, delta x, and then times the temperature u of x1t. Okay, so now this is approximately equal to the amount of energy in the rod. This is approximately equal to the amount of energy of the rod. If you divide both of those by delta x, what you get is, and use the fact that x1 is arbitrary, you get rho of xt is equal to the specific heat, which depends on x1 and u, times, x and u, times the mass density function. So I'm going to have to come down here, times the temperature, and that's it. Okay. So here, rho is equal to the mass, the specific heat times the mass density function times the temperature. Now, what we're going to do is assume c is just a function of x. Now, if the specific heat actually is a function of u, then this equation gets much more complicated. But we're going to assume that for small values of temperature, like for small temperature changes, that the specific heat is basically constant. And so the specific heat only depends on x. And so in that case, we're going to get rho of xt is equal to c of x, c of x times the mass, m of x times u of xt. Okay, then so if we look what the equation, if we put this in that conservation equation, we're going to get that the that c of x times m of x times the t derivative of u. These don't depend on t, otherwise I'd have to have the t derivative out here. If, for example, I included the u here, I'd have to have the t derivative out. This, excuse me, this is still going to equal minus the x derivative of the flux. However, Newton's law of cooling, which is just a special case of Fick's law, Newton's law of cooling says that F is equal to minus some function k times the x derivative of the temperature. And similar reasonings that we discussed for this relationship in Fick's law apply here for the temperature. Okay, and so now what we get is the heat equation now we get the heat equation if U measures if U measures the temperature of the rod, and let me put the argument here. So if U of xt measures the temperature of the rod at location x and time t, then the specific heat of the rod times the mass density of the rod times the t derivative of the temperature is equal to the x derivative of k times the x derivative of u. if the rod is homogeneous, so that C of x is just equal to a constant, and M of x is also just equal to a constant, then we can write this as the t derivative of u is equal to 1 over c times m. We can always write it this way, I guess, even if it's not constant, times the x derivative of k times the x derivative of u. And really what we can do is, since C and M are constant, we can move that all the way on the inside and get something like the x derivative of k over Cm times the x derivative of u. Okay, and now, so we can only do that if C and M are constant, and if k is a constant, I'm going to define a new function, little k. If little k, which is equal to k over Cm, is constant, then we can write this as the t derivative of u is equal to little k times the double x derivative of u. Okay, now oftentimes when we talk about the diffusion equation, we don't write it with rho, we write it with u, simply because that's just the convention. We want to think about u as being the function that we are solving for, I guess u for unknown, but we use rho as this intermediate step to get to u. Okay, so this is the diffusion, and this in particular is the heat equation in one variable. In the next video, I'm going to quickly go through the derivation of the diffusion equation in two variables. It's going to involve a use of sort of the divergence version of Green's theorem.